Welcome to Inference Time Tactics. I'm Calvin Cooper, the co-founder and COO of Neurometric AI. Really excited about this episode today. We've got Yash, who last time for our listeners, he was a guest on the podcast, and he's now joining us as our head of AI research. So Yash, you want to say a few words and before we kick things off with Carter?
Yeah, it's been exciting. I think my podcast was in November. I think I joined in January. It's been a good time. It's fun to kind of be at an early stage startup, kind of do everything. And it's interesting. I think we saw some alignment like through the podcast episode. I was talking a bit about the research I'm excited about. It seemed like that research in Neurometrics also excited about. So really cool to see like what we come up with this year.
Absolutely. So we've got a fun conversation today with Carter Huffman. He's the co-founder and CTO of Modulate. First off, Carter, congratulations on all the momentum. You released a new ensemble listening model announcement with Velma 2. And on our end, we actually put up an audio leaderboard. And so we'll talk a little bit about that today. But before we kick things off, do you want to give a little bit of your background, Carter, and what you do at Modulate?
Hey, fantastic. Thank you so much for having me. I'm super excited to be here. Yeah, absolutely. So I'm the CTO and one of the co-founders over at Modulate. So ultimately, I'm responsible for our AI research, our technology, making sure our models are the best voice understanding models in the world, which is ultimately Modulate's goal. We want to be able to understand every conversation, all voice, no matter what language, no matter what accent, no matter how many participants and what their objectives. That's our goal, and I'm ultimately responsible for helping make that tech happen. So I've got an awesome machine learning team working with me to ship these really, really great models. So a little bit of my background. Before I started Modulate, I was actually a physics major, as most, so many AI researchers happen to be. There were a lot of really, really cool parallels between kind of learning how to understand signals from the physical world, from like measurement devices, that kinds of things, that translated over to machine learning and understanding audio signals. So the parallel kind of made sense. After I graduated, I went over to the Jet Propulsion Lab out in Pasadena, California. I worked on machine learning and instrument autonomy for some of the spacecraft. So the rovers, autonomous kind of spacecraft missions that visit like meteors, asteroids, all those kinds of things, and trying to teach them to process data on board so that they don't have to ask humans for help so often. Was really, really cool. And then I took a lot of that machine learning expertise and used it to found Modulate.
Really fun. So what inspired you to start the company?
Oh my gosh. Well, I think I've always been the kind of person that loves to really dig into problems and try to understand, hey, how does this work? What's going on? Like what's kind of behind the data and behind the results that really kind of make sense to my own little world model inside my head. And I happened to get into machine learning over at JPL right when convolutional neural networks and deep neural networks really started gaining popularity. Early 2010s was a super, super cool time. And neural networks always appealed to me because initially, like just from the biological parallel with your brain coming right out of undergrad, I was like, we're building artificial brains. That's really cool. I want to be a part of that. And as I kind of dug into it more, I sort of found two things. One, I was super impressed by how powerful this stuff was. The original GAN paper, and then some of the follow-ons where you could take like a picture of me and remove my glasses and still produce like a coherent picture of myself. That was all new in the early 2010s. And I was like, that's incredible. I've never seen anything like this. I really, really want to get into it. And then on the flip side, I was kind of like, I had a day job at NASA, but it was still a day job. And I was kind of like, there's no way I can keep up with all this research on the image generation, text understanding and generation. Where can I kind of dig in and try to make a little bit of an impact that other folks aren't working on right now? And it turned out that audio, especially real-time efficient audio, tends to kind of lag up until now behind text processing, image processing, even video processing. And so when I was getting into machine learning and AI, not a lot of people were working on voice. Mm-hmm. And I really found that as a niche that I could contribute to. I started working on it, started being able to do things that I wasn't seeing any published literature about, like voice manipulation, voice synthesis, that kind of stuff. And that really kind of got me going. And I've been doing that for the past 12, 13 years.
Wow. So you started the company that long ago?
Started the research behind the company.
Research.
I think the company founded officially, in like 2019, 2020. But it
tracks.
all has a ton of heritage back to just all this like machine learning and AI audio understanding.
Yeah, I was going to say, because like back in the early, 2010s, like 2013, 14, I was an associate at a venture fund, helped raise one. And before I really got the more respect with the partners to speak up, I was trying to kill every AI deal at the time, because it was like, it was AI with like, it was deterministic. It was not true AI, right? And so what's happening now is a lot more exciting. So curious, like, once you founded the company, did you like achieve product market fit instantly, or what was your starting point versus where you are today with the product?
I wouldn't describe it as instant. We started, we kind of did. So many people do this, and it's such a challenging journey. I mean, you all know, a lot of folks know how hard it is to really start and build and keep pushing on a startup. We started with a cool technology that could do something nobody else could. At the time, what we started with was actually real-time voice conversion and manipulation. So I'm talking, and instead of me, I sound like James Earl Jones, or I sound like Katy Perry or Taylor Swift. Really cool technology. And nobody had that at a high level of quality and also being able to do that in real time. We thought, we built new technology. It's going to sell itself, no problem. We started the company. We thought our seed stage investors were investing in us because they thought, you product market fit is a shoo-in. They actually were investing in us because they believed in us and figured we'd figure it out. But we kind of were going out. We were tackling, real-time voice conversion. Where are all the places you can use this? You can use this in audiobooks, podcasts, video games, all these sorts of things. And we were going out trying to sell this technology. And we slowly discovered that there's not really that much TAM that was accessible for real-time voice conversion. But what was so promising was our ability to write extremely efficient and accurate audio understanding and manipulation machine learning models. So we found a lot of application for that, doing understanding type tasks like moderation, anti-fraud, etc. So same core technology, but very different company and product.
Interesting. So why did gaming become your first serious deployment?
Gaming has always held a special place in my heart and my co-founder's heart. We were both growing up gamers. We knew kind of the consumer side of the space. We learned very rapidly we didn't know the business side of the space and had to learn that kind of on the fly. But gaming is a really cool area because it has a ton of constraints that require interesting technical solutions. It's always been like that. Gaming really pushes hardware, really pushes technology. And one of the cool things about voice in gaming is there's a huge amount of scale and not a lot of resources available to handle that scale. If you want to process 100 million hours or 1 billion hours of speech a month, like happens in some social gaming platforms, you can't do any of that or very little of that on device, which would typically be your go-to answer, because your device is busy rendering Call of Duty. The GPU is totally booked. The CPU and RAM, these things are running their systems as hard as they can. And so you have to find those resources somewhere else. But if you're going to pay for dedicated GPUs just to run voice processing, like in a moderation task or another voice understanding task, that's a huge added expense. So you have to be really, really careful and really efficient. So gaming makes a really interesting place, challenging place, but interesting place to build new technology.
You're not saying Call of Duty hypothetically either, right? This is one of your customers.
Absolutely.
And this has a special place in my heart also. Like when I was a big gamer, I loved Call of Duty Clan Wars. I don't know why they shut that down. They need to bring it back. But this is just like, for those who don't know, it's like 72 hours of team clan wars globally. And so you're just like staying up all night and trading hours. So somebody's actively playing and just eating pizza is super fun.
And on that, I guess in Call of Duty, what tasks or applications were you applying your technology to? Were there like particular scenarios where we needed voice understanding or conversation understanding within Call of Duty and have that be in real time?
Great question. The primary application is for anti-harassment, anti-toxicity, and even more severe stuff like fighting child grooming. So what happens is you have a huge amount of voice traffic as people are socializing together, talking to each other, enjoying the game. The vast majority of that is actually quite benign. People are just having fun. Maybe they're trash talking, but it's all fun. It's all good natured. People are enjoying the game like they should be. However, a small percentage of participants can exhibit toxic behavior that tends to get emphasized on anonymous or online platforms. And so you have a small group of people who will harass folks based on their skill level, based on the sound of their voice, their perceived demographics, or for whatever reason, just because they want to ruin somebody's day. And when that happens, you end up not only alienating the person you're targeting, but also everybody else in the conversation. Nobody just wants to hear somebody like beating somebody else down and ruining that whole vibe, that whole kind of social interaction. And it makes the experience worse for everybody. And if it happens often enough, they stop playing the game. So it's a huge retention problem for gaming studios, this toxicity. And they didn't really have a way to solve it because there's so much traffic, and people will use community-driven tools like reporting, report somebody harassing, well, they'll report you back. So solving that crowdsourcing is not an answer. And solving that by just hiring a ton of moderators to listen to 100 million hours of chat a month, also not a solution. So they really needed technology to process these voice conversations quickly and cost effectively to find that toxicity and stop it.
So at a high level, what is your model actually doing when a live conversation is happening?
Great question. So the audio is coming into the model and it's immediately being fanned out to an entire set of ensembles of models that all have different specialized tasks. So you have, say, a transcription model that's trying to figure out what's the content of what you're saying. But different models have different performance characteristics. Some are more expensive to run, some are cheaper to run, some are really good at English, some are really good at Spanish, some have general applicability, some don't. So we actually have a whole ensemble of those transcription models and an orchestrator that picks between those models to figure out which models are doing the best job on this conversation live as it's happening. But if you're familiar with the voice space, you'll also know that just transcription loses a ton of the nuance of a conversation and means that if you're trying to understand what's going on, you can't possibly parse out the full meaning of a conversation just by looking at a transcript. So if I tell you, I'm having a great time right now, or I'm having a great time right now, it's exactly the same words, but the tone's totally different. It means two completely opposite things. This happens all the time in social interactions. People use sarcasm for humor, et cetera, et cetera. So we also have other models that are running simultaneously for tone, sentiment, emotion, figuring out some basic demographic information so that we can place, like, who are these people having this conversation? How's this going? We have a bunch of these different models to get a full, complete picture of all the different aspects of the voice conversation live as it's happening. And then once we get those results from all of those ensembles, it bubbles up to an orchestrator layer that's pulling all that information together and figure out what's happening based on what you're saying, who's saying it, how it's being said, what's going on in this conversation right now.
That makes a lot of sense. And I think you're pointing out something that I think is really important for some listeners in our audience. People on the more technical side really understand why you need this whole universe of model providers and ensemble models. But maybe on the investor side or the buy side, the customer side, people are like, how do I pick the right horse? Like, if it's not made by Gemini or Claude or OpenAI, I don't get it, right? And so you're really proving the power and the need for ensembles of models and specialized models and seeing the impact. So I think that's really important.
You're pointing out a really cool point with Gemini and all of these other large models, which is that those companies are taking a very large foundational approach to AI. You're deploying the biggest model you possibly can to handle every scenario that you could possibly throw at it. That's really awesome. And these are super, super powerful. But that generality and ability comes at an expense, which is literally a dollar's expense of you're running the biggest algorithm on the planet, consuming a ton of power, a ton of compute. It costs a huge amount to run these big models. And that can be a waste when you have very specific tasks in mind that don't require that huge amount of generality. And so there's a kind of a trade-off forming between a large general model that can do anything you throw at it and be super flexible versus building out a more concrete pipeline based on an ensemble of models that can be flexibly directed to a variety of different, very diverse tasks, but can optimize themselves to do those much more efficiently than just throwing a huge neural net at it.
Right. And I did want to dive deeper into like the system architecture here and also the benefit of latency. So, as I understand it, as you described it, you have this ensemble of models, and while the audio is being fed in, you're sort of tracking which model is performing better. And then through that, you output, say, that text or whatever output that model yields. So it does sound like, for example, the models could be smaller, but as you described it seemed like you're running all of the models in parallel, and then you're sort of identifying afterwards. Is there any additional complexity towards your system that, for example, if one did an end-to-end call with the larger model, the end-to-end model call is more expensive, but because of the additional complexity underlying the system, the overall system cost might actually be higher in some scenarios with this sort of fan-out approach? Could you maybe talk to that a bit?
That's a fantastic question. And yes, if you were running every single model in the ensemble on every single byte of data that's coming in, that would actually be substantially more expensive than just running one big universal model. So the trick is really to understand which models in your ensemble are producing either similar outputs or lower quality outputs, and cut those off and trim down to a smaller subset of models that still give you high accuracy and a lot of meaning. And the really cool news about this is actually that you can pair two different concepts. One is sort of general expert models that you can trust across a wide array of domains that can very quickly validate whether some of these smaller models are performing well on a given domain. So, for example, if I'm calling in on a cell phone line and it's 8 kilohertz MULA encoded, really low quality cell phone audio, and I'm on a bus and I'm talking, that's a very different audio environment from a high quality studio recording. Different models may perform with different characteristics on those audio streams. But if you have a general but expensive model that will mostly do a good job, you can run that and your two smaller models and see which smaller model happens to do very well on that domain versus not. You can run that live on the beginning of a conversation, find your performance characteristics of your models on that specific domain, and then cut out the other models that aren't providing a lot of value. And the way you cut out those models. So part 2 is actually that problem of how do you figure out which models to run and which models to cut. It turns out that we've done a ton of research sort of as a species over the past decades on optimization problems. And if you have an ensemble of models that provide a certain amount of accuracy, but cost a certain amount of compute, then you can turn those values into an optimization problem and run a classical optimizer to figure out which of these accuracies should I buy with those certain compute values, and turn it into the sort of computational problem that people have been solving really, really efficiently for decades.
Yeah, and telling that story is really important because like when we started launching our leaderboard at Neurometric, it was really because the headlines and the market's really talking about this GPT model beat this model against some academic benchmark. But in the real world, you need that domain specificity and the task specific impact of using different models and different algorithms and approaches. And so when we saw what you were doing with Velma, it was a great opportunity to put up the audio leaderboard. So Yash, do you want to talk a little bit about what we found there? And then Carter, anything about how you're performing and what it showed, what we learned from that.
Yeah, absolutely. So traditionally with leaderboards, we kind of always care about performance, like how good is this model at this task. What was super interesting about the audio leaderboard, which was definitely prompted through our discussion with Modulate and their excellent Velma 2 release, was across these different tasks, we're not only tracking performance, but also cost. And so one of the very clear things is there's this artificial analysis AMI data set, which covers multi-turn conversations. And what we found there when we produced this sort of leaderboard is that while Velma 2's word error rate might be comparable to a larger model, you even see an order of magnitudes benefit in terms of cost. And so as we're moving towards this scenario where we start to care about profitability, we start to care about real-time applications, and things which are prohibitively expensive just aren't viable solutions, mapping out both cost and performance becomes super important. And when you look at both axes, you start to see the value of the small specialized models and the ensemble approach. Carter, do you have anything to add?
Absolutely. I think there's two really exciting pieces to this. The first piece is the total amount of audio out there is over 1 trillion hours being produced every year across different kinds of conversations, phone calls, meeting recordings, etc. There is so much voice content out in the world, and almost none of it is being used for any other purpose than just somebody says something, somebody else listens, and you hope the message got across. We think that AI and machine learning capabilities can bring added value to every single one of those spoken hours on the entire planet. And if you sum that up to 1 trillion, and then you multiply by what are typical costs for even just transcribing audio, like 10 cents an hour, $1 an hour, that becomes a huge amount of spend per year. However, I think that there is a really, really cool opportunity to derive interesting, useful, even incredibly impactful results, like removing toxicity from a game or protecting a hospital from getting hacked through social engineering, where you can't spend $100 billion a year protecting that ecosystem, but you can still deliver a lot of value if you can understand that data correctly and take action on it. On the flip side, you can't spend $100 billion to protect all of these different environments and conversations, like, for example, a social gaming platform or a hospital's IT desk. You might have somebody calling in and trying to hack in, and you need to catch that social manipulation. But if you can't process that audio cost effectively, you can't run AI on those conversations and try to pick that stuff up and help defend all those areas. So there is so much content, but it's only usable and only can add value if you can process all of it cost effectively.
I guess one question that I have, I mean, there's a few we can go in directions, is this sort of cost performance trade-off, like showing that the ensemble of models, saving on cost by having a larger model, for example, grade the smaller models, then identify which smaller models working well, and then just reusing the smaller model for the rest of the audio, and then getting that cost saving. All of this seems very general in terms of methodology. It doesn't necessarily have to only be applied towards speech transcription or synthetic voice detection or even toxicity detection in gaming. And so maybe you can talk a bit towards the generality of the approach and whether this really could be applied anywhere. For example, speech synthesis, even going beyond the voice modality. And to what extent do you kind of want to, what is your focus area here, given the generality of the approach that you've demonstrated?
The technology behind large ensembles to process especially long context kinds of data, like a voice conversation, is really, really incredible. Being able to get that cost efficiency as well as that accuracy that spans a very large duration, very large context window. That being said, I think there's something about voice conversations that very particularly lend themselves to this architecture. So on the one hand, anything that has a long time horizon, like a video or even a novel, has different areas where you might have certain models perform better than other models and can get savings and accuracy boosts by deploying an ensemble instead of just one model that tries to do a good job at the whole content. But voice conversations have a lot of that. So one, voice is a very difficult and interesting kind of data to process. You have this really long one-dimensional signal, not a ton of content in each sample, but tons of different pieces of nuance that you pick up as you start looking over tens or hundreds of thousands of those samples all at once. So you already start by needing long context horizons to process raw audio, which means your models start out being very, very cost ineffective, and you have to kind of optimize from there, starting from sort of a rough default. And then two, conversations have ebbs and flows. They have intents behind the participants. Like everybody has an objective that they're going after when they're having a conversation. And so you have these really, really long time horizon things that you, one, have to process a whole conversation in order to parse that out in the first place, and two, can make an impact on how you understand any individual piece of a conversation. I can say one phrase or one sentence, and it means two completely different things depending on the entire context leading up to when I said that. So the difference in time horizons, as well as the difficulty and complexity of the underlying data, makes voice conversations a particularly good place to do hierarchies of ensemble models.
Do you want to talk a bit on like how the system works as conversations move forward? So as we were hearing before, like in the beginning, we don't really have any context, and so we just try out lots of models. Maybe we have some demographic information that kind of shoehorn into some subset, but in the beginning, we're just trying models. Then we sort of identify through maybe a large model grading it or through some intent classifier as to like this particular model seems to be working well. But as you said, as the conversation evolves, the conversation can change, and another model should kind of maybe pick up the slack. And so there seems to be a lot of complexity or challenges here. Like, how do you deal with that long context? How do you kind of pass over from one model to another model? And then, like, how do you ensure cost savings if you're kind of using a large model or a general model as a grader, but you kind of have to bring that general model back later in the conversation because maybe the conversation has changed and now you need to switch the model. And so you need to, again, restart that sort of loop that you had in the beginning. It seems like there's a lot of hyperparameters here, to use a machine learning speak. And so how did you kind of identify a system that works and works generally and is scalable? It's not services work, right? You don't have to recreate a new system every time. It seems like a very challenging problem. Like, how did you arrive at it?
Part of the initial challenge is identifying a set of models to build your ensemble from that'll cover a very wide and diverse set of experiences and data being sent through the system. So having models that work well on social chats versus phone calls versus other things, trying to combine all of that together and figure out how do I build an ensemble that can cover all of those pieces, that's a very challenging task. That being said, once you do that, and once you benchmark all of the different models on different kinds of data and how well they cross-correlate in terms of performance, as well as how much do they actually cost to run, you end up with a much more traditional optimization problem. And that's where you can start employing well-known strategies around exploration versus exploitation. So you can say, at any given scenario, how confident am I in my current strategy to exploit the conversation and do a good job producing accurate results, versus how much do I need to explore and see if either there's a better optimum that I can find through a different selection of ensembles, or if the underlying distribution has changed and starting to deploy new models can be more effective than continuing to run with my existing strategy. So it is a potentially shifting underlying data distribution, but you can apply actually very battle-tested optimization techniques on top of those ensembles once you have the ensemble itself.
I would say for like a final question, what do you see as like the current limitations of your current system. So it's Velma 2. I'm assuming we're going to see a Velma 3 or some next generation of models. Um, I mean, do you feel like there are still limitations in terms of conversation understanding that you really want to push forward? Or is there more of like a scaling out horizontally, applying this to maybe synthesis, for example? What do you see in terms of the next steps on how things can improve and what you're working on now?
I see even more possibility in the voice understanding space along two axes. One is building out more complete representations of a conversation. We aim to really build the best voice understanding models in the entire world. And what that means is right now we've deployed an ensemble of over 100 different models to piece out all these different aspects of a conversation and build up a good representation. But there's even more sophisticated behaviors, starting to get even deeper into the intents behind the different participants, the different scenarios that they might be in that could affect the conversation and what's going on. There's been a lot of talk about context graphs. Why are people making decisions that they're making? Being able to turn a conversation into a context graph and build that out live as it's happening, and also have that for posterity and sort of build out an understanding and kind of causal data set over time as you have more and more conversations. I think all of those are very, very fruitful areas to expand the capability of a conversation understanding model like Velma. And then on the flip side, the more time you spend building out more specialized, discrete, and optimized smaller models, as long as you continue to employ a good optimization strategy, you can push down cost and push down latency even further. So I think even though on the one hand, our models are some of the most cost effective on the planet, I think there's still a lot more to go as we continue to push that research and make voice processing even more accessible to any budget.
Awesome. So for listeners who want to dive deeper, we're going to link to some of Modulate's research, the Velma benchmarks, and the Neurometric audio leaderboard. If you like this episode, please be sure to like, share, subscribe. Carter, thanks for joining us today. And thanks for tuning in to Inference Time Tactics.
Thanks so much. It was great to be here.